Let's rock. Hello, everybody. I'm Wojciech Burkot, currently with Bait Tech. Some of you know me from the past stints here, and some from GeeCON also could have heard my other talk like 2 years back, and frankly, I have absolutely no idea why, screwing that one badly, I got invited to give another one. We'll see how it goes. I tend to digress a lot when I speak, so in order to stop this and give you a chance to ask for things which interest you, I marked some of the statements in the presentation with these small asterisks. If you see one and you are in for the digression, just show your hand or shout or do whatever so I notice. And then I can go on the tangent marked that way. I'm going to talk about quantum computing, trying to convince you that it is actually right up into the mode where we can start think about programming those beasts. How it all started. We should start with some definitions, right? And that's something which people have been thinking a lot about. Frankly, I disagree with most every single one of those, maybe except for number 5, saying that the quantum computer is a computer that is able to capture the full computational power of quantum mechanics. Why is that so? If you think about the Moore's law, how the speed of the processors, transistors, grew recently, if you think about this plateau around 2006, where it looked like this growth is slowing and people started talking a lot about this slowing, actually that was quantum mechanics and the availability of the FET transistor with tunneling gate, which brought us up to the Moore's law curve again. But this is not about so those transistors actually use the intrinsically quantum mechanical properties of silicon in thin layers, and that's what makes them run. So we are actually experiencing the power of this word in devices which are used daily, I would say. However, this is not the full power to be had. So let's see what can we get once we harness the full power of quantum mechanics. And of course, it will be much easier for me to talk physics here. And yeah, I was warned not to do this. So let's try to go with some marketing hype. What you see here is Gartner curve. People tend to estimate the progress of technologies by categorizing the progress into several stages or areas. And this is a particular way of presentation of this curve. If you think about any individual, just because it's Gartner, right? They want to cover the word broadly. If you think about the individual technology, you can plot almost the same graph, except that the time scale will be just in the time it took this technology to reach the broad market. That's not me. Quake, wow, in Krakow. No, quantum, yeah, quantum quake. All right, so how to, I don't know, frankly, I don't know where people from Gartner they get data from. I'll be really surprised seeing where they place some of those technologies. Especially, and that's again something from my past, if I'm using my personal, and it's like trademarked, I've seen already people using this, but I thought that was really cool and funny when I started. The best approximation for the Gartner curve is Google Trends, right? So let's see how the quantum computing looks on the Google Trends. Quantum computing is the blue line. Sorry for the misleading title. And being curious, and that comes actually from the previous talk, which I really botched up. You might ask, what's the red one? And the red one is the search term DevOps. So it looks like there was a run for DevOps, while for the last couple of years, the quantum computing looks like it is in actually really, really interesting place. Where is this pattern with the minimum within the horizon, right? It looks like we are about to reach this slope of enlightenment if this approximation is any good. So this is the same thing in on the slightly different time scale. And you can see that you can tell many things about the interest in quantum computing, except that it is actually growing. However, it is interesting from the other perspective. If you think about any other technology and how money is made on the technology, actually there is a lot of money on the sidelines. You can see that as the investments in the AI thingy. Don't get me started on that one. There is no asterisk here. And the second generation of, for example, Google processors intended to run AI in the cloud only, just announced at Google I/O. But you know, as well as I do, that the NVIDIA and others are really strong in that game. So there is a lot of money to be spent on the technologies which are promising. And I just took the survey of media last week. Frankly, people who know me know that it wasn't exactly last week. It was more like yesterday. And that was the news in yesterday's media. D-Wave, yes, there is an asterisk. You might want to try that one. Not necessarily here. There will be more opportunities for D-Wave. Just got additional $30 million for development of the next processor. They are currently at something like 2,000 qubits, and they plan to use this money to grow to 4,000. For those not accustomed to those numbers, there are two things which need to be said here. That change means that the power of D-Wave computer will grow 2 to the power of 2,000 times. That's the growth they are planning. It's not just doubling. It is the exponential law here. Except that we'll get to that the qubits used and designed by D-Wave are really, really poor quality. And we'll talk about this later, what poor quality means in this context. Nevertheless, their technology of running their systems close to absolute zero and being able to cool their processors and isolate them from the environment is to be laudated. So D-Wave, very big growth, and it went in the shadows of this announcement, but you can also check the recent news by the China Academy of Sciences. They just got the proper, well-corrected and stable qubit number 10 in their quantum register. This means doubling the power of the largest quantum computer, not being the adiabatic machine as D-Wave is. And as I said, this was like the news from 2 days back. Was it any different? Meaning, did we see the chances that we are on the rising edge of the Gartner's curve? That's how the world looked like in 2015. The biggest players, D-Wave, about 1,000 qubits, adiabatic qubits at that time. Google, there should be plenty of asterisks. If you want some of the backend stories, you can get them here. Google just started getting benefits from acquiring the group of Professor Martinez from University of California in Santa Barbara, with completely different concept to what was within Google about the quantum computing. Google at that time actually used D-Wave, which seems to be, rather than a commercially available machine, as it is claimed, to be some sort of the trophy computer. You are rich and powerful, you get the D-Wave machine, right? Google used this for two things. One was training the classifiers for image search, and the other one was actually training the user interface for Google Glass. This didn't really went far, and other commercial companies who attempted the use of the D-Wave for their real-world optimization problems, like logistics within large warehouses or robotic TSP, forced TSP, notice immediately that those machines are way too small, trying to solve the optimization problems by adiabatic cooling of some other initial state. At the same time, people at IBM, notably, and there is an asterisk, you are not using this, so I might actually end faster. People at IBM, notably Chad Rigetti, came up with something which everybody knew, that there was an actual quantum computing machine on the back-end side. On the front-end side, though, you got the web interface looking something like the Lego play box, where if they trusted you, you could actually put those small boxes representing quantum gates onto 5 wires representing qubits, and create some limited experiments. IBM thought that that would be the best way of programming quantum computers at that time. They made that available. Fast forward to today, they closed this kind of approach to their systems, claiming that there were something like 40,000 experiments run on the quantum experience. Of course, if you tried to run this, you needed to sign the kind of NDA transferring all the IP rights to IBM, for whatever you come up with. Luckily, the 5 qubits were way too small to do anything useful, so nobody really cared. Or some people use students to play their algorithms. Students not having the IP rights to them couldn't transfer to IBM. So that's how this play was run at that time. There were serious limitations. Namely, if you think about the measurement, you can see that actually there's a double line coming out of the measurement box, meaning that you can't do something which is extremely important case of actually usable quantum technology, namely quantum key distribution. Without acting on the measurement result, you can't do the teleportation, which is at the core of those algorithms. So this was kind of limited. At the same time, there were some suggestions that the actual quantum machine on the back end was larger than those 5 qubits. With some limited technology, nevertheless, it was available. So big things were happening already back 2 years back. About the same time, you know, maybe you don't know, the prevailing technology for quantum computers is QUIL as a basic unit, which is 2 Josephson junctions cooled to near absolute zero and actually using superconducting currents to control them and actually to read the data. So that was the development stream, except for some very odd things in Martini's group. Everybody else was trying to do squids, despite the fact that there were, at least theoretically, trapped ions, photonic quantum computers, theoretically possible. And at that time, the group of Professor Peter Smith from Southampton University, buying their stuff on eBay, really. His group, his PhD students, were buying stuff to support their lab on eBay. And out of sudden, they come up with the quantum computer, or at least the basic building blocks for the quantum computer, based on light. So laser being able to get entanglement, so like photonic interactions, and they got a lot of money. So you can for the future developments. So you see that this is still a place where there is no grown-up technology. Nobody really knows how the real quantum computer would look like when it is operational. You had another chance of asking about the D-wave, seemingly large one, but no means no. So those guys are using light and lasers, and once they publish their results, we're getting quantum gates with fidelity way better than anybody else. They got tons of funding, really tons of funding. So it's not only government agencies, it's also private sector who invests a lot, thinking that it's possibly the next big thing, and that it requires a lot of money to actually run those experiments. I kind of promised that there will be no physics. There will be like 3 slides, and this is the most dense one. So we are trying to get the basics of the quantum computer to programmers. There are just 2 operations which you can do on the quantum computer. The first one is unitary time evolution operator applied to the state. Nothing more than just multiplication by really huge complex matrices. There is nothing else in this formalism, and there is nothing else the quantum computer can do. The state of the computer in time t+1 is the state of the computer in times t multiplied by the huge unitary matrix. Unitary, that's the generalization towards the complex numbers of just rotations. So it's really, really, really simple. You can think about those as rotations in the complex space. The other thing the quantum computer can do is just it can respond to a measurement. Measurement in quantum mechanics, this is this part which is spooky, which spooked Einstein when he learned about this, and where the probabilities come into play. Actually, what you'll get as a result of the measurement is one of the eigenvalues of the underlying Hermitian operators, which are in turn aligned with the physical observables, but you get one of those values with certain probability. Those probabilities can be calculated. This is extremely precise science, but this is still probabilities. So you can't assume that you will get the particular result with 100% probability unless the operator you are measuring has just one eigenvalue. This has some consequences, and this is slide number 2 on physics. You can think about the qubit as a 2-state system where the weights are complex numbers. You can think about the quantum register as the right tensor multiplication of those individual qubits, except that you can run those transformations on the pairs or triplets of qubits, meaning you can get the entanglement. The state will know that in some other part of the register, it has some values. That's a state in that complex space, which gives us immediately exponential capacity, which we talked about. The quantum register of the length n can hold 2 to the power of n different states simultaneously. So for us programmers, it looks extremely useful. You can have extreme single instruction multiple data just because you act in the single clock on all the states represented by register. Looks rosy, it looks like you can get exponential speed up on anything just doing brute force, properly representing your data in those registers. Regretfully, there is this measurement part. In order to get any useful information from this system, you will need to actually measure the register. And then, if you are using just a brute force, then your chances of getting the results you want are exponentially small. And the balance between those 2 things is something which is at the core of all known algorithms using quantum computers. You might have heard of Grover search, and you might have heard about Shor factoring algorithm. The first one is interesting because it sets limits to what unstructured brute force approach can do. You will get approximately, you take any known classical algorithm and you are getting a quadratic speed up over this. And there are ways to actually design that given the classical algorithm. There is another nice, maybe not so nice consequence of the unitarity of the evolution, namely no cloning. You can't copy a state. Otherwise, you, clever programmers, will immediately see how the backtracking could work, right? You want to search for a particular solution, you just brute force represent that in the register, you measure, you are not getting what you wanted, you backtrack, since you had a copy of the state, and you repeat the calculation until you get what you wanted. So it would work, except that there is no cloning. You can't clone a quantum state. If you try to write even on a single qubit, if you try to write the appropriate equations for the really simple matrix multiplication, you'll see that there's no unitary transformation which can copy a state. And there is some other physics getting in, namely, those states are fragile. If you look at them funny, they just disappear. This is called decoherence, meaning that the entangled state in the whole register will fall apart. You can measure individually, you lose correlations between those bits. So what can we do? If we are getting to the next part of this talk, if you are to take home anything from this part, is that quantum computers will not solve hard problems by just brute force and using the parallelism which is there. Yeah, I'll flash that another one time, so that's the important part. And that's the nasty details of physics. The right-hand graph, the upper part shows something which people were trying to do the error correction, like using the IBM quantum wires and the gates on them. It kind of works, but let's see what does mean on the right-hand side. Essentially, you are getting the probability of finding your qubit in the state it is supposed to be at the time of the order of tens of milliseconds. Looks like your computer will be pretty slow by today's standards, and looks like the fidelity is not there. So what people come up with was actually error correction, but pretty clever. If you think about the state, let me use the analogy here. You know about the electrons in the conductors, you know about holes in the conductors. Think about the hole as a quantum system. It's way easier to describe the behavior of the hole-dominated conductor rather by describing a hole as a quantum system than describing all the electrons with that missing one which are there compared to the crystal lattice of the conductor. So you can either do the regular error correction, pretty classical, or you can do something else. You can create artificial states on the lattice or in the single line and try to evolve those. If they are designed properly, they will live much longer than the individual states, just because they will be using some rules of exclusion. How people come up with this? Here are two competing results. One, you'll see the IBM 4-qubit, 4 physical qubits, 1 logical qubit, or even 4 physical qubits, 0 logical qubits in that one. So you are getting just the error correction, you don't get any data. Kind of weird, but that's how they designed their first system. On the right-hand side, you see the linear approach to this, a line of 5 qubits holding the data of a single one. Why is it important? Just because those things don't tend to last long, and here are our needs. So horizontal double lines are the resources needed. In order to do the classical computation, you'll need a certain number of qubits. If you want to do quantum chemistry, like the protein folding, that kind of thing, You'll need slightly more if you want to run the proper machine learning, even more. If you want to break RSA with 248 key using Shor's algorithm, you can do this, of course, but the number you will need to have is something like 10 to the fourth of qubits you can operate with, meaning logical qubits. And just like in any integrated circuits, a single bit in the classical processor is done by several transistors, depending on the implementation. It looks like in quantum realm, this multiplication factor needs to be much higher, and that's where the tangent lines, what the tangent lines show. Actually, at the very top is actually existing today a adiabatic qubit of D-wave computer. Still, their quality is not enough to get useful calculation. Physical, non-adiabatic, you see the other line. That's how that word would look like, unless there is some breakthrough. So I see that many of them are border enough. Yeah, another chance. How do you program those things? So first approach would be to limit yourself to the boxes applied to either 1, 2, or 3 quantum wires or qubits. Why is it up to 3? Just because you can prove that the universal gate is 3-input gate and in the quantum world. And you can approximate any gate in any dimensional space using just 3 of those. So you can either play with the boxes, or you can go and think about how it would look like. So then you will have to have an abstraction, like the Turing machine, or for the classical world, or quantum Turing machine for the quantum world. Those guys, and you can see the name, Rigetti Computing. Nobody asked, but still I'll tell you. This is the guy who stood behind the IBM quantum experience. He designed those chips. Then he left IBM and he founded his own company, initially on pretty low VC investment. Now he's getting tens of millions. Again, this is a cool thing to be in, so people are spending money on this. Those ideas in this talk, coming from this place onwards, are according to the setup they provided, just because it's way better than IBM, and it's easier to collaborate with another startup than with a large company interested in getting as much IP as they can. So this abstraction is slightly stronger than a quantum Turing machine, which you can find across the publications. And they come up with the language, and we'll make fun of the language shortly. Essentially, the extension is ability to get and gather classical data, measurement results, other data, parameters to drive the circuit, which is illustrated in the graph shamelessly stolen from his publication. What is the quantum abstract machine? A fixed number of qubits, fixed by arbitrary. You can program any size of the quantum computer. Then the definition, the same thing about the classical memory. This thing has classical memory to store the measurement results, to store parameters. There is a number of the fixed gates, so the gates which behave the same way regardless of any parameters, and the fixed number and list of the parametric gates which can be modified. The action can be modified by the classical parameter. Parameters are usually complex numbers. That's not the end of the list. Here's the continuation. Program, meaning a sequence of arbitrary sequence, finite, of instructions. And the program counter, meaning where we are in this program. Sounds pretty straightforward. Sounds like something which was back in 70s, and you'll see how the language reflects that. And those 6 numbers are the state of the quantum machine. So you see part of the state is classic, part of the state is a quantum state. You can, and here's a hope, just like with IBM, and IBM desperately wanted to kill this idea. After failing, they actually killed theirs and joined the club and started using the other languages to program their quantum chips. And they hate Rigetti for a good reason, right? An implementation, the second bullet under the bold line is important. An implementation on quantum hardware is called a quantum processing unit. Looks like, and nobody will tell you that at this moment, that somewhere in Rigetti's lab there is an actual quantum processor used by them to experiment, as well as the virtual machine which is available via web, much bigger than the one made available by IBM, still limited. If you get a full state of something like 20 qubits, it will be difficult. You can get some information about this size, and it looks like the problem is with the size of the container in the implementation they use rather than anything else. Still, you can program this beast, either the virtual machine or the actual one. Programming, you need a language to program, right? And the language of choice here is a quantum instruction language, QUIL. It reflects available 1, 2, and 3 qubit unitary operations. Again, good place to ask question if you want. Reflects measurements and their impact on the state. If you yes? Can you repeat? Okay, I will. Thank you very much. If you think about this space, exponentially large space with the basis vectors defined by the individual qubits, any combination of them is a basis state. There are 2 questions here. Essentially, you operate on the whole register. So what does it mean that you define your operation on a single wire, single qubit, or 2 qubits? It means that you are essentially multiplying that effect on the given qubits, that's why you have to name them, show their position in the register, by a unity operator on everything else. So this is called rising, this is called leveling. Essentially, this is a tensor, right-hand tensor multiplication of those operators. But you are multiplying by 1 on every other qubit than this one, and this creates action in the full space of the register. And 3 in the parenthesis, yes, the work by Tommaso Toffoli back in 90s showed that the universal quantum gate has 3 wires, but you can approximate any quantum gate with exponential precision by having just 2 wires. That's why it's enough to get the 2 input gates, and the part of approximating the transformation of the whole register with what you provided in the program is a part of the compilator here. I don't know why. So here's an example. It's extremely simple. You have 2 qubits. One is a control one. The other one is controlled. On the state of the first one, the second one gets inverted. Full stop. There is nothing more. And you are seeing just a part of the appropriate matrix representing the operator. And there are ones on the diagonal everywhere else on any other. And those matrices are exponential in size, right? In QUIL, in the language, you'll see just C0 JK. It is important to realize that you can actually swap any 2 qubits If you think about the physical interaction, they need to be close. So the gate acts on both of them. But it can be shown that any qubits which are not adjacent can be brought together by the series of reversible permutations, which are just 2-qubit operations. So the whole matrix thing is irrelevant. You can just, in QUIL, you can just write C0 JK specifying the position. What else in programming? Every gate is defined separately from its invocation. So you define first, and then you use. Gate can be either static, doing always the same thing, or parametric. You can define the gate P name, and the parameter, single parameter it has here is just a complex number. And it acts on 3 inputs, E, J, K. What else? Every gate is defined separately from its invocation. There is a language statement, def gate, and you can just define everything you need, and only then you can use this. Remember the colorful blocks on wires? You can define circuits, meaning groups of gates. They would be applied sequentially to the state, and then you can do that with the language instruction def circuit. What else? As we said, there is a need for having a way to measure things, and there are 2 uses for measurement in quantum computing. One is just to reduce the state, as we told, to get that projection. And the other one, sometimes used for the error correction. And the other one is, so you are getting the permanent measurements on 1 or 2 qubits, which affects other qubits, and so they behave. Essentially, that's how the continuous quantum error, yes?
Are these measures totally deterministic? Or is there some kind of probability?
Of course, there is a probability distribution coming from the system, and this is a part of the compiler to calculate those probabilities and give you the result according to the probability distribution. If you run this thing on the real hardware, then obviously it comes by itself. The measurement will be probabilistic in nature. Of course, you are exactly right.
Do you get a chance of setting with what probability you want? What's the margin of error you are able to?
It slightly depends. If you think about all the transformations you might have done in the calculation prior to that moment, there are certain limits to those probabilities, right? Like if you run the Shor's algorithm on this machine, you'll get probability nearly 1 on finding the right state after the prescribed number of steps. So those probabilities are calculated. I do believe you might have an input on the distributions or the random number generators behind this. But this is like, if you measure a single qubit in the after applying Hadamard, you'll get the equal probability of it appearing in both possible states. But if you do something with it, more deterministic, you'll get some other probabilities. So yes, you have control, but it is limited by physics, right? 2 kinds of measurements. First one, measure 5th qubit. The second one, measure 7th qubit and store the result in the classical memory bit number 8. How would the program would look like? Yeah, if you ever programmed, whoever, please, give me a show of hands. Who has ever programmed in any assembler language? So yeah, thank you very much. I'm kind of surprised, and you see that essentially the guys are still back in 70s, right, with what they propose. And indents are crucial. 4 spaces, otherwise it doesn't work, right? For real, it's part of the definition of the language. jumps. Some of them are physical, some of them are not. So you'll see the invalid jumps. I don't want to go through the whole language specification, but you can see that it is pretty ancient. Yeah, the language supports pragmas, and luckily for us, some of us, there is an interface, right, which is written in Python. So you can program reget this quantum computer using Python libraries, getting what you wanted. But essentially, it will translate that to, it will generate the QUIL program, and then it will do what it has to do to approximate the gates you are using, and then to execute the code either on the virtual machine or in the real one. Another circuit doing exclusive OR. Yeah, if you ever program assembler, there is nothing interesting here. But there is something interesting, I guess, in this summary. So eventually, it's not only big guys, it's not only IBM, it's also startups who started thinking about the whole programming environment and actually made that available for use and practice. And somebody else, and this is a nice abstraction layer on top of the actual quantum computing hardware. We don't know how the real quantum computer would look like in 5-10 years. Everybody's claiming that they are very close to having a real one. Google says, Martinez actually says, in 5 years. Some other guys, D-Wave says, in 2 years will be 4,000 qubits. Other guys are making strides towards the architecture and towards the working quantum computer at larger scale, but you can't tell what it will be in those coming years. If you think about this approach, there is an abstraction layer on top of the actual hardware. So your programs, if written in QUIL, most likely would run on any hardware which is kinda reasonable by the time it exists. That will be the final slide of my talk, just something which I need to say. There is also a quantum computing startup here in Poland. I have a pleasure of working in it, a couple of us, and we got the support, I guess, on the same basis as D-Wave got, except that we are not getting tens of millions, slightly less, and in zlotys, not in dollars nor euros, but it is still substantial. So, and the private sector is also extremely interested. It's funny, actually. You focus on your own work, and you are getting requests from VCs who have absolutely no idea what they are talking about, who want to invest in your company. So, if you think about getting practice in programming quantum computers, you can as well start now. Thank you very much. If you have any questions, I hope I can answer them. If not, thanks again.
May I answer a question?
Sure.
Ask a question. You mentioned several physical implementations and how operators...
Where are you? I can see.
I'm here, yes.
Okay.
How operators are implemented in that systems?
It's different. In the squid-based, this is just an inductive loop running between the different qubits, which seriously limits the topology of the connections you can get there. Physical is physical. You can shift states and do the swap, which is supported by this language. But essentially, the topology of the graph, meaning what is connected with what, is limited in those systems. You could see that very clearly in D-Wave, for example, and you might have come across the paper claiming that it is the fastest whatever since whatever. It was really indeed fastest in just one thing, emulating D-Wave processor on D-Wave, which kinda is easy, I would say, once you get the D-Wave. So yes, this is one of the situations. The other one, photonic interactions, that's actually pretty cool. The guys from Southampton built a bunch of lasers emitting light synchronously, and they placed them on the physical structure in the shape of the cone or the pyramid, meaning that there was a fixed shift between those sources, meaning the light was able to interfere at the very low level. That was different implementation for completely different things. There were other approaches using the pseudo singlet states in solutions and then using nuclear magnetic resonance, but it was shown that actually you will not get the entanglement in any larger scale. The largest adiabatic one I know is the Chinese one, being able to factor something like 247. It was last year, so maybe they are something in the order of 500 in their factorization efforts using still different technology. Welcome. Thanks again.